graphons, mergeons, and so on. Suppose we want to cluster this data. First, we must decide which clustering algorithm to use. There are many choices, and it isn't always clear which is the best for our particular application. Once we've selected an algorithm, we have to choose its parameters. Here we often use a rule of thumb or an educated guess as to what will work. We then feed in the data and examine the output. How do we decide if the result is good? Usually we apply a sort of informal eye test, and if the clustering doesn't look satisfactory, we tweak parameters or use our next favorite algorithm until we obtain something we do like. But even for a good clustering, it isn't always obvious what interpretation one should give to the clusters. The point of this is to say that clustering is often ad hoc. In some sense, this is because the definition of a cluster is somewhat vague. But there is an approach to clustering in which the notion of a cluster is clearly defined. This is the statistical approach. Here, we assume that the data is generated by an underlying distribution, such as a density. We then identify the clusters of the distribution itself. The goal of clustering is then clear. We want to recover the distribution's clusters from a finite sample. In this work, we develop a statistical theory of clustering for graphs. Here, the task of a clustering algorithm is to organize the nodes of a graph into clusters. We assume that graphs are generated from a powerful non-parametric random graph model of much recent interest called a graphon. The term graphon is short for graph function because the model is defined by a symmetric function mapping the unit square to the unit interval. We can interpret a graphon W as a sort of weight matrix of an infinite graph. The weight of an edge between nodes x and y is encoded as W of xy. By interpreting these edge weights as probabilities, we arrive at a procedure for sampling adjacency matrices for unweighted, undirected graphs of any size. We begin by defining the clusters of a graphon. Our notion is similar to that of the connected components of a graph. This results in a tree of clusters, which we call the graphon cluster tree. We encode the height at which pairs of nodes merge in this tree using a special graphon, which we call a mergeon. Clustering in the graphon setting looks like this. The input to the algorithm is a finite graph sampled from a graphon, and the output is a hierarchical clustering of the graph's nodes into a tree. We introduce a distance between the graphon cluster tree and the output of an algorithm, which we call the merge distortion. It compares the height at which pairs of nodes merge in each tree via their mergeons. An algorithm is said to be consistent if it converges to the graphon cluster tree in our distance. This raises an important question. Which clustering methods are consistent, if any? In this work, we produce a consistent clustering method. A key step in the algorithm is the estimation of edge probabilities in a graph sampled from a graphon. In total, our theory suggests solutions to common problems in clustering. There are many algorithms for clustering graphs, but when the graphon is a good model for our data, we should consider choosing an algorithm that is provably consistent. The merge distortion provides a way of measuring the quality of a clustering. And we may interpret the clusters produced by a consistent algorithm as estimates of the graphon's clusters. To hear more about graphons, mergeons, and so on, please stop by our talk at NIPS, which will be given on Tuesday, December 6th from 10:40 to 11 a.m. in Area 3 of the Convention Center.